Hello. As part of the micro and smart systems course, we were discussing the modeling techniques in the last several lectures. This is the last lecture on the modeling of microsystems, and we are going to talk about something slightly different from what we have been discussing in the modeling part by highlighting the scaling effects that we find in microsystems. As we discuss the scaling effects, we will try to look at the modeling issues, and it will serve as a review of the modeling that we have discussed so far. Let us look at this pressure sensor device that we have discussed in the lecture that we had on sensors, microsensors. If you look at that slide here, we see that the sensor is over there. In fact, it is an exaggerated picture where the chip is shown to be larger than what is surrounding it. It is not a scale drawing per se, but if you just see that the final product which is shown here, which is a pressure sensor made by Motorola, it is a commercial device. The chip will be quite small, that is over here, this is the chip, but the final device is going to be big because it has to be interfaced to something at the large scale where human beings can handle it. So, one can ask the question, if the final product is going to be big as we can hold in our hand, why should the chip be so small? The same question can be asked about some other devices. For example, this array of micro mirrors which we had discussed earlier in one of the lectures, where we had talked about modeling, where the torsion beam and how to take care of the modeling of the torsion. Right. Now, if you look at this device, there is an array of mirrors, small mirrors, as you can see, the ones that are shown over here, several of them will be there, and they tilt and project the image. If you look at the computer projector that uses this array of micro mirrors, again a commercial product, that is quite a large box, and one can ask the question, if the final box is going to be that large, why should we make this mirror array at the micro scale? Again a pertinent question. The final device is going to be big, but the chip is small. Why should we do it? Here is another example of another mirror array. The previous mirror tilts about only one axis, whereas this one can tilt about two axes, and here the purpose is, as again we had discussed in the earlier lectures, you have a number of fibers here, and they all need to transmit to a number of fibers in the output fiber bundle. So, these mirrors that are over here and here tilt, so that every one of them can go tilt there and come back and address any one of them. So, if you think about how big this system is going to be, or device is going to be, the switching device is going to be, it is going to be quite large, because there are going to be about 1000 fibers here, 1000 fibers in the output. So, you need to connect all of them. If you take the connector size and the whole alignment fixture that is made to position these micro mirror chips, it is going to be quite large, definitely of the order of tens of centimeters, whereas the chip itself will be quite small, a centimeter by centimeter. So, one can ask the question, why should we make the mirrors so small? This has to do with the scaling that depends on many things. So, let us look at motivation for miniaturization. Now that you have heard a lot about microsystems and their fabrication techniques and modeling, now let us look at the reason for why people try to miniaturize things. The first reason, of course, that you would have already guessed by that time, is the economy that is associated with making things small, especially if a product that we are looking at has a large volume, that is lot of products are made. If you make several of them on a same chip and subject it to the same processes one after the other, the cost per chip will come down in that batch production mode, and for the same reason that IC chips have become very inexpensive and the cost of them keeps going down, the same thing is likely to happen for microsystems as well, and that is why there is a strong reason for making things small, even when all applications do not require that micro size. The second reason is that some of these micro devices might not even work if they are made any larger. Okay? That is a point. So, there are some phenomena which work only at the micro scale through miniaturization, whereas in some others the scaling is such that it favors miniaturization. There are a few devices of that kind as well. And if you think about what are the really driving factors for making things small, it could be the weight, which is very useful in consumer applications where you carry like a mobile phone and watch and things like that, or in aerospace applications where weight is of concern, and power. Power and energy are critical for almost any application. So, if you make things smaller to do a job that can be done by a larger one, if it consumes less power, which is always the case, then there is an advantage. So, there are a number of reasons, and one of the most important reasons is that if you use an array of identical element, we basically get the advantage of VLSI, very large scale integrated systems, like imagine an army of ants actually lugging a big insect or a food that they eat. So, that is kind of an analogy we would like to take. A lot of them, like a micro mirror array, one mirror probably will not be of much use. With an array of mirrors, it has a purpose. So, there are many reasons for miniaturization, that is why we make it small, but really the driving factors are the scaling. So, if you make things small, things do change, and there are advantages most of the time, sometimes there are also disadvantages. We will look at the scaling issue in a number of domains today, and this will serve, as I said at the beginning of today's lecture, as a review of the modeling that we have discussed. The first is mechanical domain, and then we look at the thermal domain, electrostatic, magnetic, fluidic, optical, biochemical, acoustic, and power. So, all these domains have something to do with scaling, and we will discuss that and then see how we can use very simple modeling arguments to answer this question, why miniaturization in all of these subfields. And finally, we will spend some time talking about what units to use when you do computations, because that is a question that arises whenever we try to do some modeling, because your numbers may become too small if you start putting 1 micron as 10 power minus 6 number in a computer. So, we will discuss that a matter concerning the units to be used in calculations. Okay. The first thing when you talk about scaling is to realize one very simple scaling law, and that says that volume related phenomena decrease much more rapidly than surface related phenomena, which in turn decrease much more rapidly than length related phenomena. So, if you look at this scaling law, pictorially is illustrated here. You have the macro world here, this is our blue world, and then the pink world is a micro world. Macro world, length looks very tiny, you can hardly see it there, surface looks a little bit bigger, volume looks very large, and it is exactly other way around at the micro scale. Length looks really big, surface medium, and volume is hardly felt. Okay. So, the way to see is that length is L, surface is L square, where L refers to the size, L cube refers to volume. If there is a large number, 10 becomes 100 becomes 1000 for volume, whereas if it is 0.1 it becomes 0.01 and 0.001. So, anything to do with length related phenomena is going to be dominant at the micro scale, and then comes surface and then volume, and the reverse is true at the macro scale, where volume related phenomena is going to be very influential, surface less influential, and length related phenomena will be least influential. This is the basic scaling law that we should keep in mind as we discuss the modeling related to microsystems. Some of these is very well embodied in if we call it science fiction, in Gulliver's Travels, which many of us or many of you would have definitely read about and enjoyed the amazing tales of Gulliver. And if you just think about and read that book between the lines now, you will see that there are a lot of nice scaling arguments that were put forth by Jonathan Swift, the author of Gulliver's Travels. Because he says that when Gulliver arrived in Lilliput Island, they had to decide how much food to give them. If they eat certain amount of food, since he is 10 times taller than them, does he eat only 10 times more food or is it more than that? And they decide that it should be 1000 times more food, because compared to what they have, their size is 10, but volume, which is the volume of the stomach to fill his need for satiating his hunger, has to be proportional to the volume, and that is how the food has to be decided. So, there are many more arguments in that book, and people have thought about the scaling for a very long time, and here we are showing a couple of sketches that were taken from a book by Galileo Galilei, who was one of the first people to conduct experiments systematically on gravity. He had also thought about scaling, because he observed that compared to the animal bones in small animals, this is the bone in a small animal and this is the bone in a large animal. He made one observation, Galileo made observation which is quoted here, taken from this reference, Dialogues Concerning Two New Sciences. And he says that the large animals' bones look bulkier compared to their length aspect ratio is quite reasonable, whereas the bones of small animals in the same body part, let us say a leg, it looks much slender. Why is that? Why is the proportion changing from length to the area of cross section in small animals and large animals? Okay. We can answer this question from the mechanics viewpoint, as we will see. And this kind of analysis is actually there in almost everything, not only in nature scaling analysis, but also in engineered structures, which goes under the name of allometry, differential growth in the body parts or even engineered things depending on the size. So, they say that everything, let us say a parameter x, if you take, it is going to vary with an exponent beta, and there will be some proportionality constant alpha, as if we take x as a size, at different sizes y will vary. So, they have given these exponents in this particular thing, a nice book by McGowan, From Diatoms to Dinosaurs, the reference if you want to look up more on this topic, how surface area changes in the biological things. Exponent is 1.95, almost 2 as it should be, and heart weight, heart rate, liver mass, they all have different exponents, and for the length as well as for the mass. So, this allometry also helps, and one can do these allometric things for pressure sensors, compare the large scale ones and the small sized ones, and then see that they also satisfy an allometric relationship such as this one. This allometric relationship exists for nails also. If you look at the diameter of the nail compared to its length, it is not linear. So, if you plot it, it is actually a log plot which you cannot see very well. This is the nail length and this is the nail diameter. This is a log plot. So, if something is linear log plot, actually it means that there is exponential relationship in reality for the normal thing. This again another nice book on size and life by McMahon and Bonner, where they say that even for engineered things such as nails, there is a allometric relationship. So, there is a scaling law involved in things that are made in different sizes. So, now we will first pose some questions and answer them now. The first one is, when you think of microsystems, should we worry about the self weight? Civil engineers you know have to worry about self weight, but should microsystems designers worry about self weight? Are inertial forces always negligible? Why is electrostatic force attractive, and how about magnetic force, is it attractive, and thermal actuation, is it favorable or not, and microfluidics. We had one lecture on the fluids, but now we will see some more examples of modeling issues in fluids as it pertains to microsystems. And optical phenomena, optics and microsystems go very well hand in hand, but there are places where miniaturization does not make sense in optics at micro scale. and we look at power generation and whether the scaling is favorable there or not, and chemical and micro reactors. So, what does scaling mean there, and biological applications and acoustics and even manufacturing and power and so forth. Let us start with the first question: is self weight important in micro devices? Okay. Let us say I am making a bridge like this. This is anisotropically etched cavity and there is a bridge over this. Should we worry about the scaling, should we worry about self weight in this case? So, here we show that delta is equal to some formula that we know from strength of materials or from Castigliano's theorem that we had discussed in the earlier lectures. So, if I try to get this delta as a relative deflection by dividing it by the size L of the beam here, this is the deflection, relative deflection due to its own weight, and we see that it is proportional to L. All others here alpha 1, alpha 2 are proportionality constants. So, B is alpha 1 times L and H is alpha 2 times L. So, it depends on alpha 1, alpha 2, and finally, we see that relative deflection is proportional to size. That means that relative deflection decreases with size. If I look at this, a beam of 1 meter length and a beam of 1 micron length, the 1 micron one is going to have much less relative deflection. So, that is, if I divide this delta deflection by this L, then I would see that it does not, L and capital L in this slide are the same, that relative deflection will be much smaller when you consider micro one. So, you can say that self weight does not matter so much when it comes to microsystems devices. But then is inertia force, because weight is inertia force, can it always be neglected? And let us before that, let us come back to this Galileo's bones and then see whether Galileo was right in his observation that large animals have bulky bones as well as small animals have slender bones. He looked at, in fact, in his passage he refers to the strength, because generally if you take bones, whether it is a large animal, small animal, the strength is not going to vary much. It is the same bones and bone strength will be pretty much the same, but he observed that the stress is proportional to the size. Okay. That is due to self weight. If an elephant is standing on its 4 legs, it has to hold, the 4 legs have to hold its weight, and the same thing is true with the mouse. But then the stress is proportional to the size, meaning that if you say from mouse to elephant, it is 10,000 let us say factor in terms of its height. Now, the stress in elephant is going to be 10,000 times more than what is there in the mouse. So, you have to have bones of elephant much bigger and bulkier than that of mouse, and that is what is the scaling argument that tells us when you design something at micro scale, you have to keep in mind the scaling argument, otherwise we could make mistakes. If you say that the self weight, which is an inertia force, is negligible, we do not need to worry about it at micro scale, but what about other inertia forces like centrifugal force? If something goes let us say spinning, there will be centrifugal force on it. In the context of gyroscopes, we had discussed that. Should we worry about these inertial forces that come because of rotation structures that are rotating? Here is a picture from Sandia Labs, which is a gear train. These gears turn at a very high speed. Even though their weight or inertia is quite small, the inertial force is going to be quite large because the speed is very large. So, if you think of this wheel going at a very high speed, when these might sit on them, they may actually fly off, because the inertia force is very high on them because of the speed more than their own weight. So, when you consider dynamics, which we had a very small introduction in the context of vibrations and resonance frequency and other issues in this discussion modeling, but if you consider the dynamic response in general, we have to include the inertial effects, otherwise again we get a wrong answer. And another thing that we need to remember when we model microsystems is that smaller things move faster than the macro things. It is an everyday experience for us that compared to its body size, an ant or any other insect moves much faster than the animals including ourselves that we know. That is because whether it is a solid or a fluid, things tend to move much faster at this small scale. That can be understood by looking at just this cantilever beam that we see here that vibrates like this. That is a frequency of vibration that we had taken as the natural frequency and discussed in the context of modeling the vibration effects in microsystems. That frequency, if we look at substitute the values related to the size, we see that frequency is proportional to 1 over size, where L refers to size. That means that when you go for small scale systems, your frequency is going to be large. When the frequency is large, things tend to move fast. That is the notion of something oscillating. If you take if the frequency is high, it will go very fast, if the frequency is low, it will go slowly. So, consequently, because of its favorable scaling, people have built a number of dynamic devices such as this micromechanical filter, such as a band pass filter is shown here. This is a band pass filter, which is a mechanical filter which goes to very high frequency. The one that is shown from the work of Professor Clark Nguyen at the University of Michigan, but here it shows that the bandwidth is 15 kilohertz and the base frequency is 7.81 megahertz, but people have gone much beyond that to few gigahertz just because of the scaling. The smaller you make it, the larger the frequency becomes. And we had also discussed the residual stress effects in the context of modeling, and we said that residual stress or stress gradients are not so important for the macro scale structures, whereas for micro scale structures they are very important. You can use them to your advantage, or when you do not want any bad effects due to the residual stress, we have to definitely model so that the effect is not felt significantly. And we had discussed earlier in the context of actuators whether we should go for electrostatics or electromagnetics or thermal or other types of actuations. We had argued that electrostatic force is favored at the micro scale or for miniaturization, and for that we had taken this comb drive, other type of electrostatic actuators, and made a simple calculation. In the discussion we had on modeling electrostatics, we had derived formula for deflection due to electrostatic force. Now, we just recalling that formula for the comb drive, where there are a number of combs and things go in between, and this kind of motion we had said the force is proportional to this quantity. There are number of is equal to that quantity, number of combs, permittivity, thickness and voltage square, and this is the gap. And now again if you take the relative deflection, we find that the relative deflection due to a given voltage is specified, is proportional to L raised to minus 2 or 1 over L square, that is equal to 1 over L square. That is, when the size is small, the relative deflection is very small, very large, because 1 over L square, whereas if the size is large, 1 over L square is very small. So, you do not get much deflection. So, if I use electrostatic force at the large scale, that is the scale that we live in, we are going to get a very small deflection relative to the size, but when we make things smaller and smaller, we tend to get a large relative deflection. Other way of seeing it is that the voltage required to achieve a certain delta by L, a relative deflection, then that voltage is proportional to just the size. The size becomes more, voltage is more. If I need 1 volt at the micro scale to actuate something to get certain relative deflection, when I move to let us say meter scale, I have to multiply by 10 power 6, 1 micron to 1 meter, then the voltage required become, instead of 1 volt here, a million volt. Million volts we will not use it in an actuator for day to day things. So, there is clearly an attractiveness for electrostatics at the micro scale, and we had discussed this magnetic actuation. So, we will not talk about this again. It turns out that if you look at magnetic force between two coils, then it proportional to the size raised to 4 and or proportional to square of the size, which is not attractive for miniaturization. Whereas, if we use a powerful magnet, then one can manage and get a large magnitude of force with micro things, and that is the trend that we see where you put a permanent magnet and put a coil to generate magnetic field in the presence of permanent magnetic field, and you can get some magnetic based actuation force. So, it does not really scale well, but one can make lot of pumps and valves and so forth, such as the ones shown here, by using a permanent magnet. That is the key to making magnetic actuation work in practice with substantial force. So, you can actually make coils, as we had discussed earlier, with a trick in microfabrication process topologically equivalent to what is a coil can also be obtained at the micro scale. Let us say we consider thermal actuators, something that we had discussed briefly in one of the last lectures, one of the previous lectures. Here thermal actuation also has, it is favored at micro scale. The absolute force is quite large and it is easy to achieve, which we do not use that much at the macro scale other than using bimorphs with two materials. But here, as we had discussed this particular device in detail earlier, but one scaling effect that we did not mention then is that if I were to make something thermal actuator 10 times larger than what it can be done at micro scale, you get that much more relative deflection. At the meso scale, which is the 10 times larger from here to here, 10 times larger than the micro scale, compared to relative deflection here, this relative deflection is 10 times more. So, we are now considering the fact that sometimes you do not need to be at the micro scale, you actually need to go to what we can call meso scale, that is let us say 10 times larger than this. If maximum size here is 1 millimeter, here you can go to 10 millimeter centimeter size and you may actually get better performance. There are examples of that kind also. We do not need to always miniaturize, that can be answered through modeling. Here we can do thermal modeling based on the previous lecture. You can relate to this device where we have different temperature distributions that tell you how this actuator is going to move and by how much it is going to move. There are modeling techniques for it, very simple modeling techniques, both actually electrically, thermally and elastically, mechanically. You can have small models to understand these effects and accordingly design the device. If something is not suitable for miniaturization, that should not even be attempted at the micro scale. Now, let us discuss a few more things with regard to the thermal aspects. You might have wondered, why do elephants have large ears and dinosaurs fins? What do they have? Large animals tend to have large ears. The reason for that is it has to do with the dissipation of heat, because temperature rise due to metabolic heat produced in animals. You can approximate it. This modeling is all approximation, a good approximation. It is the power produced P and the thermal resistance that the animal has, and that is equal to, the thermal resistance is 1 over HA, where H is the heat transfer coefficient, because if you are producing heat, if you need to take it out, it is through our skin that it goes out, our surface area. So, large animals will have lot more heat generated, P will be proportional to specific power that they produce times volume of that. Large animals will have larger PV, so larger P, and then HA, if the area, as we said at the macro scale, the volume looks much bigger than area. So, you do not have sufficient area. One way to have sufficient area is to have these large ears for elephants and other large animals, as well as with fins that are there for dinosaurs. Okay. That explains why we need to worry about cooling at large scale. At small scale it may not be, but it really depends on the application. So, we have to look at the scaling carefully. So, this heat transfer coefficient in animals increases actually non-linearly with size. Here with our simple relation based on the temperature rise we said is linear, that is not true in practice. We have to take all this modeling more carefully to see how it varies. See, large animals have larger surface area in the form of ears and fins and other body features to keep them cool, but small animals have the other problem. They have lot more surface area than the heat that they produce. So, they lose heat and they cannot be warm blooded animals anymore, they will get cold. So, they have to increase their metabolic rate, that is the P has to go up there in order to make the temperature reasonable. So, they should not get too cold. So, some of the small animals will eat a lot to have the high metabolic rate, and that is something that again is given as a allotropic law, the size related scaling. And it is there in fluidics. In fluids normally there are lot of non-dimensional numbers which do not have any size related to them, but then the value of that number makes a lot of difference. So, one example is Reynolds number. It is the ratio of the inertia forces to the viscous forces, and that is proportional to L square, meaning that if L is small, the size. So, again remember that L refers to size. If L is small, for small sizes Reynolds number is going to be extremely small. One consequence of Reynolds number being small is that turbulence does not occur. So, when you put two liquids together, they will not mix very easily, they will go side by side for a very long time, and whatever mixing that occurs, if you do not take any special care, occurs only by diffusion. So, mixing is a very difficult problem in microsystems, and in fact people say that insects actually swim in air rather than fly, because inertia forces are not big compared to viscous forces and they feel really sticky. It is like swimming through honey for small insects, although we think they are flying in the air. And we mentioned diffusion. If things were to mix on their own, it is because of diffusion between two different liquids or the occurrence interface, things go back and forth, and that diffusion coefficient, if you think, that depends on Boltzmann constant K, temperature, viscosity, material property and aerodynamic radius. And if you consider the effect of diffusion, if you consider a molecule that diffuses over 10 micron distance, okay, it goes a million times faster than it goes over 10 millimeter. First 10 microns it goes very fast, after that it takes a long time for it, which is embodied in this formula. You can see here x is proportional not t, but square root of t and square root of this diffusion coefficient d. So, at very small sizes diffusion is enough for simple mixing to occur, but if they have to happen at large distances, you have to have special techniques for stirring things and mixing things at the micro scale. One more thing in fluidics that we had mentioned in the context of modeling fluids is that this no slip condition. This no slip condition is a very important one, that again depends on the a non-dimensional number called Lucent number, which is the ratio of the mean free path of the particles, that is the distance average travelled by a particle between its successive collisions with other molecules. So, that is a this Lucent number. If it is very high or very low, we go from very rarefied things, that is we had used single atom or single molecule based simulation, as opposed to very small Lucent number, means that mean free path is very small compared to the length or size of the part. There we can use this no slip boundary condition, whereas for other ones we had used slip boundary condition or otherwise modify the fluid mechanics behavior. And we had said that any actuation force that is proportional to the length related phenomena is going to be dominating at micro scale, and that is why this insect can walk over water. some people call it Jesus insect because it can walk on water. So, this happens because of surface tension. At a small scale, since a length related phenomena, it dominates over the self-weight, centrifugal force and several others. So, the viscosity effect and surface tension effects are very important in fluids. And in capillaries, when things rise in a small tube, it will rise to a higher height than a bulky tube, again a consequence of sizing or scaling, where we have another non-dimensional number called bond number, which is the ratio of gravitational force to surface tension. If surface tension is high, then the bond number will be lower, and the scaling effect becomes not so important, but the surface tension related forces dominate at the micro scale. So, you can actually make things move using surface tension. To relate to our daily experience, if there is a small mustard seed lying on the ground, how do we pick it up? We wet our hand, put our hand over the mustard and pick it up, it will stick. Imagine doing the same thing with the football. You have to put maybe thick glue and stick the football to your hand and take it up, but whereas just a little bit of wetness or moisture with water can pick a small mustard seed or cuscus seed. That is happening with actually surface tension force, because at small scale, not with the football, with the mustard seed you have the advantage of using surface tension effect to pick things up very easily. This surface tension being a phenomenon that is proportional to length, that means it is very favorable at micro scale. A number of researchers have used it effectively to move things at the small scale. Making a pump and a valve is not easy at the micro scale, because there are moving members and there are sealing issues and lot of performance issues, but if you can move it without having to use pumps and valves, it will be very advantageous, and that is what several groups have done. You can look up the papers published in several journals where surface tension is used effectively. And here we need to talk about the contact angle. So, if I take a substrate and put a drop, this is just a drop of a liquid of some kind, it could be even water. If the contact angle, which is this angle, so if I have the surface and if the drop is like that, only mercury and normal surface will be like this, but even a water can be like this and a hydrophobic surface. If I take this angle, that is the contact angle. If that is large, then we have an advantage in the sense that this drop does not wet the surface, and one can actually change this drop takes this shape because of surface tension. You want to minimize surface tension. The contact angle depends on the drop, what is inside the drop and what is there in this substrate. Usually it will be like this. Now, if you apply either an electric field or a thermal field, this drop might become shrink like it is shown here, or can bulge also. So, using this effect of creating drops, making them smaller and larger, you can have a grid here and make each of these bubbles go anywhere in the fluidic network that is shown here. This is the fluidic network. In this fluidic network, we see that the drops can be moved by just varying surface tension by applying a electric field. This is called electro wetting. So, if I take a drop sitting on a substrate and apply electric field, I can change the contact angle. What is like mercury drop here becomes flatter, that means it has flown. Now, if I put these electrodes all across these things, okay, and activate one at a time, we can make these drops move. The drops can be cut, they can be merged, then they can be moved. So, merging, cutting and transporting, all of these things can be done, including generation of the droplets to begin with. So, you can use these drops to move things around on the chip, and that happens only because surface tension. We cannot do it at the micro scale. So, that is really a consequence of scaling. Now, if you look at optics, this is let us take a different color. If you look at this, this is really the visible light spectrum wavelength. It goes from 400 nanometers at 0.4 microns to 0.7 microns, 700 nanometer, and that is exactly the range where microstructures can move. So, you can manipulate light like it was not done before, and there are a lot of devices. So, we had mentioned this polychromator application in one of the lectures, where by just moving these beams up and down, we can get this interference based way of generating from white light any light of certain wavelength that you desire. So, with that correlation spectroscopy done, and that is a principle of this polychromator. And there are many other examples where optics and MEMS or microsystems go so well together that there are a lot of advantages, but here is an application where miniaturization is not favorable for an optical application. This has to do with an absorption spectrometer, that is, you send a light of certain wavelength to a chamber that has certain gas that you would like to detect. Then when it goes through that, this light is absorbed by the molecules of that gas that you want to sense, and that can be detected. So, the light has to be inside that chamber for enough time. If you make it small, it does not have that time, so you may not be able to reliably detect. So, if you look at what happens if I miniaturize this, which some people have tried to do, they found that there are problems. So, if you look at a 100 micron spot of a laser beam, let us say, just over 1.6 centimeters, you can put a lot of mirrors and increase the path inside the chamber, that is not a problem, but as it reflects off one mirror to another mirror and so forth, its spot size is going to be diffuse and become bigger, its size increases by 100%. But if we take a larger spot size, it increases only by 3% over the distance 1.6 centimeters. So, it makes sense to go for higher spot size here than lower. So, it is an example of miniaturization that is not favored in optics. It is very rare, but there are examples. Now, when we go to acoustics, there is again a lot of scaling, and the way microphones are designed, one has to keep in mind that as you make microphones or micro machined microphones, we have to keep the frequencies and other things in mind. So, you see that the elephant trumpeting will be very different from a mouse chirping or a bird chirping or a mouse making its own noise. So, they are very different frequencies. This is low frequency and this is high frequency. We have the frequency on this axis and this animal mass here. Small animals have high frequency and large animals have low frequency. So, we have high frequency here and low frequency, that has to be kept in mind when we look at acoustics. And here is an example where the scaling was exploited with microsystems, and this has to do with the digital production of sound. Normally, when we say sound is digital, it is only in the way it is stored, but not in playing back. Here we normally use this analog microphones where there is a membrane that moves back and forth as it is shown here to generate a signal. It has some problems because dynamic range or bandwidth is not very high, and nonlinearity is a problem, and fault tolerance because the membrane breaks, you do not have a speaker or microphone, and controlling intensity is also not so easy. So, somebody came up with an idea that if we have speaklets, each of them gives a small sound, okay, little quantum of sound. If I want to have 4 times that, I will make 4 of these go off at the same time, and if I want to have a no sound, I make it 0, 1, one of them, any one of them. So, you get the fault tolerance that was not there here very easily with the digital production of sound. Here again we have a array of the identical thing doing something useful. One speaklet, that is speaker, small thing, we call it a speaker, one little membrane, all of them are linear range, but they can produce any signal with respect to time. So, there are advantages of using miniaturized one, because you can do all these tricks, individual speaklet membranes that can produce any sound of any frequency and amplitude, and still there is redundancy and the fault tolerance that comes with it. Now, let us look at the biological and chemical microsystems. Why is miniaturization necessary there? One, when it comes to biochemical analysis, is that you can get away with small sample sizes. So, you can do combinatorial analysis, that if you want to see one drug and want to test it on number of combinations of drugs, you can do that. And we said that things move faster at small scale, you will have quick analysis. We had looked at blood sensor, which is a handheld blood sensor, which is a commercial device. There you can get the result in a matter of minutes, as opposed to now going to the lab, giving you a blood sample and going the next day or later in the day to collect the result. This will be much faster, almost at the point of care, that is doctor's office itself, we would know the result of a blood test. And cost effective and disposable, that is another advantage of making things small. As we discussed, there is an economical advantage, because they are small, not material is there, you might as well throw it away rather than keep it. And drug delivery can be done by implanting, and you can have all kinds of integration that can be done when it comes to why we want to miniaturize chemical and bioreactors. In chemical reactors, if you want to get the optimum rate at which chemical reaction takes place, getting precise control over temperature, pressure, concentration, other factors that are there is much easier at a micro scale or small size than at large size. So, you can use the chemicals in optimal fashion. And sample size cannot be too small also. There is a simple calculation that we can do. The sample size that you need to take is given by in a work published in the literature. Let us say that it is 1 over efficiency of the sensor. Let us say that is certain efficiency, that also varies with the size. The same sensor made at large scale, small scale, efficiency will not be the same. Let us say if we set that aside, how many species you want to detect something in this small drop that we have here, how many, if you want to detect a virus, how many virus will be there, that depends on Avogadro number and the concentration. So, if you want to take a V sample that is very small, if it is that very small, then the concentration also is going to be very small. So, for a given concentration, you are not going to have many species. So, you might actually miss even if it is present, and that will be a problem. So, we cannot make sample very small. There is advantage in making it small, but too small will lead to problems. And here there is a small capillary putting all these drops. The last row is quite difficult even to photograph, the paper says, because even before you take a photograph, this drop will evaporate, because if you take a small volume, because the surface area is more than it is at the macro scale. So, it will just lose its moisture or content, water content, and it will dry up. So, that also needs to be kept in mind. So, a lot of scaling effects what we need to keep in mind when analyzing these micro systems. Here is a slide that we had talked very briefly in the context of actuator discussion, where today you can generate power on the chip. This is really power on a chip, because you have one chip, several chips on single wafer. It is a complete gas turbine engine that is made on a thing that is like a short button size, 21 millimeter in diameter, 3.7 millimeters thickness, something which has a turbine, compressor, combustion chamber, everything. So, there is a lot of interest now to produce power on the chip with some fuel that is convenient to carry, so that we do not have to rely on batteries. Now, if you look at miniaturized devices, battery occupies a significant size in the device, mobile phone being a classic example, because the battery, if you remove it, feels much lighter, and in fact, if you can make the battery small, mobile phones can be made much smaller than what they are today. So, if you can generate power somehow, or come up with a fuel for the power, this particular one uses hydrogen as a fuel, some other fuel which is much lighter that you can carry and put it there, there is an engine right on the device to produce the needed power. That will be very interesting, and that particular aspect, that is this designing power generation on the chip, requires modeling that is very sophisticated, and it would not be an exaggeration to say that it is as sophisticated as the designing a Pentium chip or AMD chip that does this fantastic computation that we see in the computers today. And finally, we said that we will discuss the units that we need to use when we do calculations or when we model numerical calculations of the microsystem modeling. So, if you take a meter as a meter or a micron as 10 power minus 6 meter, you have to put in a very small number into the computer, and that might make when you square it, cube it. For example, in width, if I take moment of inertia goes as let us say depth of the beam cube, if depth is taken in microns, let us say 5 microns, if you put 5 into 10 power minus 6, that raised to cube, it will become 125 into 10 raised to minus 18, which is a very small number, and if you that multiply by another small number, there could be round off errors, truncation errors. So, we have to use appropriate scaling for the length, and the best way to do that is to go to dimensions. There are 7 fundamental dimensions: the mass, length, time, charge, temperature, mole and candela. Mole for the quantity of atoms, molecules, and candela for light. So, now if we take any quantity and express in terms of these dimensions, we will know. Our interest is to see how it depends on the length. Okay. If I take let us say permittivity, that is epsilon naught, because I would decide that let us say microns, I will put 5 microns as 5 number in the computer, then what would I factor do I put for epsilon naught? The best thing is write down what are going to be the dimensions of epsilon naught, in particular for the size turns out to be minus 3. That means that if you put something to be a micron as the unit, then you have to multiply this by 10 power 18, because it is L raised to minus 3. Similarly, voltage will be the size is L square. If you have let us say 1 volt, actually you should put it as if we are doing the scaling of the length by a factor of 10 power 6, you put it as 10 power 6 raised to power 2 or 10 power 12 as your voltage. Similarly, resistance has again L square. So, 5 ohms will become 5 into 10 power 12, because if we are scaling the length by a factor of 6, that has to be done. So, we have to multiply whatever that L raised to A, whatever that A is for when you write the dimension for that particular quantity. When you put into the software program or any simulation program, you have to multiply by this factor 10 power 6, if that is what you are doing. 10 power 6 raised to A, you have to multiply and put it in. When you take it out, you have to do 10 power minus 6 raised to A, so that your calculation will be correct. Deciding the right scaling factor, scale factor when you do computations is very important, and some of the software programs do it on their own, but it is always good to watch out, so that we do not fall as a prey to numerical truncation and the round off errors. So, there are the scale factors that we have for density, Young's modulus, residual stress, resistance, resistivity and permittivity, permeability in the case of magnetics, and voltage we already discussed, and magnetic field, which does not depend on the scaling, which goes back to the point that you had made in the case of magnetic actuation. If you use external permanent magnet, it actually makes sense to make things at a small scale. So, it comes out from a simple dimensional analysis that we show here. To summarize what we have discussed, scaling decides the performance of micro devices, and some of these will not work if they are made larger, but many of them they are going to perform better because of miniaturization. And another thing is that the scaling effects provide an opportunity to look at modeling in a very insightful way. It is an opportunity to learn modeling of electrostatic or other coupled systems at micro scale, as well as understand the scaling effects and answer the questions what happens when we make something very small. And in this modeling lectures that we have discussed in the several lectures in the past few lectures of this course, we discussed the coupled modeling, because when it comes to microsystems, several energy domains interact with each other, and that leads to certain challenges in simulation. And we have discussed just a little bit, I must say, because this is introductory microsystems course. We have just seen the tip of the iceberg. There is a lot more to be learnt in the modeling, but the one thing to remember is that we have to know the domain knowledge. Strength of materials we have to know, fluid mechanics we need to know, electrostatics we need to know, electromagnetics we need to know. Knowing all of that is difficult, yet we have to make an effort to understand the basics and put it all together to have a complete understanding of microsystems before we model and simulate and eventually design, make and test the device. Thank you.